So if you remember, in our external flow situation, we have flow coming in over a plate. As you move in position X, eventually you're going to get to the point where the shear stress in the flow, due to the really thick boundary layer, is small enough that it can no longer suppress the momentum part of the flow. And you get this uncertainty, instability. You start getting turbulence that shows up. So the same thing can happen here. Of course, like you could have turbulent flow developing in a pipe, but it only will happen if it happens before the boundary layers meet, right? The laminar boundary layers meet. So we want to calculate what is the distance that's required for turbulent flow to develop, what's the distance required for the boundary layers to meet, and compare those things, and then we can decide whether or not flow will ever become turbulent in a pipe. So just doing that real quick, we said here, so here we said that X FD H, we'll call this H laminar, right? So X FD H laminar is approximately equal to 0.063 D sub H times the Reynolds at D sub H. Okay, and then when does it become, when would it become turbulent? Well, that's going to be when the critical Reynolds number, RE crit, is equal to rho times U infinity times X crit. X crit, that's the position at which it would become turbulent divided by mu. So then X crit is just equal to RE crit times mu over rho times U infinity. So if X FD H laminar is less than X crit, then flow is laminar. Right? It will never become turbulent because it just will never get to the point where the shear stress is low enough that it can become turbulent. So, okay, that is a little helpful, but let's keep going with that a little bit. So we want to know, when are those, like what would be the actual length at which we would have that cutoff occurring? Another way of saying it is, when are X crit and X FD laminar the same value? Because that tells us the Reynolds number at which this transition would need to occur. So let's write it that way. Let's look at the case when X FD H laminar is equal to X crit, and decide what is our critical Reynolds number. Okay, so this bringing in what we had before, 0.063 RE DH times DH is equal to X crit was RE X crit times mu over rho U infinity. So let's see, let's bring the mu rho U infinity over to the other side, and we end up with RE D sub H times rho times U infinity times DH over mu was equal to RE X crit over 0.063. Okay, so now actually over here we have RE DH here. That's the Reynolds number expressed in terms of DH. We have RE DH here again, right? So we actually have RE DH squared on the left-hand side. So great. So that becomes RE DH squared is equal to, so RE X crit, what was the Reynolds number for external flow that we used to decide when it was going to become turbulent? It was a specific number. It was 5 e to the 5th, something like that, 5 times 10 to the 5th. So that's our Reynolds number expressed in terms of position along the duct or along the plate in this example, at which the shear stress is going to not be sufficient to keep the momentum forces in check. Right, so we bring that in and then we divide by 0.063. And this gives us a RE/DH of 2,800. Okay, so that's saying if I have a Reynolds number that's about 2,800, I'm likely to develop turbulent flow. It's going to become turbulent before the boundary layers meet, and once it's turbulent, it's turbulent. Right. So actually, this 2800 might kind of look familiar. You might see it as 2300. You might see it as maybe 3100, something like that, depending on the book or whatever. But it's in this range, and what you want to do is, if you're designing some system, you don't want to design anywhere near this, right? You want it to either be clearly laminar or clearly turbulent, because if you're designing in this region, you actually don't know what's going to happen. You might end up turbulent and have a huge pressure drop in your system where you were expecting it to be laminar. So you always want to avoid this region when you're designing. Yeah, actually, one thing. So just recall the fact that when we calculated RE in terms of delta M, so our Reynolds number expressed in terms of the boundary layer thickness, we decided that, okay, that was rho times U infinity times delta M over mu. Back in our analysis, we decided that critical value, RE delta M crit, was something like 3,500. Okay, so if you go back in your notes, and I'm sure you will, go back in your notes and look at that, you'll see that those two numbers actually are pretty close, right? That expression of Reynolds number, the critical Reynolds number in terms of boundary layer thickness, well, it should be close to the expression in terms of the hydraulic diameter, because the hydraulic diameter is determining what the boundary layer thickness can be in a duct like this. Okay. Let's see, one other thing that I kind of want to sketch out here. So in terms of transition to turbulence, so let's actually draw the velocity profile in a case where we are transitioning to turbulence. So let's see if I can get a nice rectangle. Okay. So in a case where we're transitioning to turbulence, before we get to the critical length, let's look at what that actually looks like. So let's say that this here is X. No, sorry, let's not do that. We'll just leave that there. So let's draw the boundary layers as we're growing here. So we have some boundary layer that's growing. Let's say at this point, this is the point at which we become turbulent. So what's going to happen to the boundary layers when it becomes turbulent? What I mean is, how quickly are they going to grow? It's going to grow really quickly. You end up having something like this and something like this. So once you transition to turbulence, the boundary layers actually very, very quickly will converge to that center line, just because the turbulent viscosity, that is like how much effect does the turbulent eddies, how much do they affect the velocity of profile of fluid that's far away from them? That becomes big, and so you have this effective viscosity that's big. You have a very fast boundary layer growth, and pretty quickly after you become turbulent, it's going to converge to a single value. This is the center value there. So let's draw the velocity profiles again. So this, let's say here, this is going to look something like this. We're still in laminar. Right, so we have this velocity profile like this, where in the center it's constant. But what's the velocity profile look like once we become turbulent? Maybe kind of know. So first of all, we have this, I'll draw it this way. We have this viscous sublayer. Right? The viscous sublayer is going to form down here. So we have a viscous sublayer that's forming, and that, if we remember, is where basically all the velocity gradient is. That's true whether it's external flow or internal flow. So if we draw the velocity profile, it's actually going to look something like this. Where you have this really steep gradient right next to the wall. And then away from that viscous sublayer, if you take the time average velocity at any point, it's going to be basically constant. Okay, and as you continue to go in this positive X direction, that velocity profile is not going to change, because we're not changing anything about the average boundary layer thickness as we go. We're not changing shear stress profiles as we go. You know, there's chaos due to the turbulence, but it remains constant. Yeah.
Does the viscous sublayer not grow in X?
So it'll grow until this point where you actually meet the boundary layers, because at that point, you're going to have, I don't know how to explain it. So like in this region, in the turbulent region, the turbulent forces are going to not be changing as a function of position anymore because they can't grow. Right, so you essentially come to this, it's like you have the viscous sublayer is trying to grow due to the molecular diffusion. The turbulent eddy region is trying to grow because it's constantly, chaos and moving around. They come to some kind of truce, right? The forces end up balancing for the growth of the viscous sublayer versus the growth of the turbulent region. So at the point of being fully developed, this viscous sublayer will stop growing. Okay. So that's what the velocity profile looks like. If we look at the shear stress, plotting the shear stress as a function of position. So this is tau, this is our local shear stress. We would see shear stress at the surface, tau s. So we would see that, yeah, as we first start, we're going to have shear stress that's dropping. We have a very high shear stress. As you get to a turbulent transition region, you kind of start going back up. And then once it's fully turbulent and then fully developed, right, that shear stress at the wall is not going to change anymore. And this gets exactly to that question. So this shear stress for XFD, right, is not changing anymore.